In order to understand evolution, you need to know a little bit of chemistry, and you need to know a little bit of geology and a little bit of math, but not a ton of any of those things. What I want to do today is to talk a little bit about how geologists have put the ages on rocks that we use. Now, this is important for us in studying evolution because we want to have a sense of how much time has elapsed for looking at how animals or plants or other groups have changed over time. Now, one of the things that I really love about teaching geology, about studying geology, is like almost more than in any other class I've taken, it can really affect the way that you actually see the land. And geologists love road cuts. Geologists love any opportunity to see something like this, where there's what's called the geomorphology, like the surface features of the land, and here covered with all this green stuff. But occasionally you get these little glimpses of what's happening underneath. It's like using a stethoscope or an X-ray to see what's happening down below in the rocks. And so geologists spend a lot of time reading the rocks. Now, today we're all familiar with this idea of plate tectonics, which is an explanation for how it is that continents have moved around in the past. I'm not going to unpack this whole story, but there are a couple of interesting things that I want you to know about. First of all, it actually mirrors some of the facts begging for an explanation trend that we see with the study of other parts of science too, because early on in the late 1800s, a geologist named Alfred Wegener noticed this concordance in shape, say between South America and Africa, and just like every school kid has noticed how they fit together. But what's funny is, for generations, every time somebody would say, "Oh, it looks like the South America could fit into the side of Africa," the answer was "Yeah, weird, huh?" So Wegener found a lot of evidence besides the mere shape similarity of the continents. There were certain kinds of fossils that were characteristic of rocks and the rock layers themselves that were characteristic of places in among both these continents. For example, this Synagnathus here, that's what's called a mammal-like reptile or a synapsid, just like Lystrosaurus. These two things that weren't mammals yet, but they're kind of coming off their lizard ancestors, where you find them both in South America and in Africa. And Lystrosaurus, indeed, going across three continents, Africa, India, and onto Antarctica. This plant Glossopteris, the leaves you can find in fossil beds across all the southern continents. And even this little lizard called Mesosaurus, which by the looks of it, we think was a marine animal. It wasn't very big. It was about 1.5 feet long. So this is not the kind of animal that's going to be able to make a transatlantic voyage. So there was all this evidence pointing toward continental drift. So continental drift is the fact the continents have moved around in the past, but what it needed was an explanation, and that explanation is the hypothesis of plate tectonics. So how the process works is like this. We know the Earth has a rocky core, which is hot, under pressure, and also generates heat through the decay of radioactive minerals. There's a really thick layer around it that's called the mantle, and that mantle is made up of these, this liquidy rock that's called magma. What we see is that thin, brittle crust up at the top can have, as heat rises and magma squeezes up through cracks in the crust, it's going to cause the deposition of these new layers. And at places here, at these mid-ocean spreading centers, you see the new rock getting pushed laterally away from the place where it's being formed. The effects of how this ends up looking at the land are, if we're looking at a continent, so now on the figure on the right, if you look at the land, you see that as the mantle upwelling happens, you start to kind of split apart the rocks there, and you end up with these rift valleys. Rift valleys where you tend to have deep lakes, and actually East Africa, where a lot of human ancestors are found, there is also a lot of deep rift valley lakes that are present there as well, because Africa is also currently rifting into two continents. And that's going to start to push these crustal continental blocks away from one another. In the middle panel, this is showing like a later stage where enough space has built up there in the Rift Valley where it's going to get infilled by seawater. And then near the bottom, this is more like what the Atlantic looks like today, where you have Europe or Africa on the right side and North America on the left, where you're seeing new rock being deposited in the center at the Rift Valley, but then the older rocks kind of trailing along the continents. We see a slightly different pattern when we're looking at convergent margins. So the divergent margins are the ones in the center of this figure where the mid-here Pacific ridges would be. But as the as one plate becomes subducted underneath another one, it's going to cause the release of magma and result in these little island arcs like Hawaii or Japan. And that's part of the reason why. And also, it's going to result in the buildup of a lot of earthquakes. So that ring of fire in the Pacific Ocean is largely the result of having the Pacific plate on one side getting subducted under the Asian plate, and on the other side getting subducted under the North American plate. So in this little panel on the lower right-hand side, what that's showing is, as you see the kind of this sort of squeezing and then relaxing of the coast. What happens is, as the plate gets shoved under, the tension builds up, then it pops out. When it pops back, that's when earthquakes happen. Over time, geologists have been able to reconstruct what Earth would have looked like in the past, and also what it could look like, kind of project what it could look like in the future as well. I'll link to a video that you can check out for that. But if you look at the top part of this figure, you see North America and Africa kind of mashed together as a part of Pangaea. This breakup of Pangaea happened later in the Triassic period, where we start seeing the birth of that Atlantic Ocean. But the Atlantic Ocean didn't start all at once, and it didn't actually start in the position that it is today. And actually, we have a lot of evidence for how Pangaea was built, as well as how the Atlantic Ocean opened up just here in Massachusetts by itself. A couple things to notice here when you're looking at Massachusetts. There is there's like what looks like a big lake in the middle of it. That's actually not a lake. It's a man-made reservoir called the Quabbin Reservoir. It's where most of the communities around the city of Boston get their water from. And then there's a north of Springfield, there's a interstate highway called I-91 that goes up that way. But that's in this valley that is actually a remnant of the initial stretching out of the Atlantic Ocean. But let me tell the story of building Massachusetts, because one thing that's really cool about this, briefly, is that they're actually representatives of 3 different continents that we can see looking at our own small state here. This is what the Quabbin looks like when you're there. One of the things that's interesting about it is it really does look like a flooded valley. Like, there really aren't like beaches here, because there's been no time for like erosion to happen, and because basically the trees are holding on to the land. This was flooded around 1940. The Connecticut River out in the out in Western Mass there, that's basically the low part of this basin, that actually where the Atlantic Ocean was starting out. And those mountains that you can see in the back, like the Holyoke Range doesn't look like much, but at the time, after they were formed, they're about the height of the Himalayas, so they're actually just very, very old. Another thing I should just throw in here is that at these early stages during the Rift Valley stage, there are all these rocks that are exposed in particular kind of tilted fashion, and they're old sedimentary rocks, these old mudstones and sandstones. And one thing we actually have a ton of in Massachusetts is a lot of dinosaur fossil footprints. There are almost no, to my knowledge, there aren't any body fossils known from Massachusetts, with maybe 1 or 2 exceptions, but there are thousands of dinosaur tracks that we have from this period of time. So here's part of the story, is in addition to the big continent Laurentia that turns into North America today, there's a small little sliver of a microcontinent called Avalonia, where we can find these rocks that all have similarities across the maritime provinces, down to New England, as well as out into Western Europe. So when Pangaea was coming together, this Prototethys, that was the ocean that was before Pangaea closed up, Africa mashed together this little microcontinent called Avalonia and into the eastern part of Massachusetts. On the other hand, what happened later, if you look on the right-hand side of the screen, that's obviously the east coast of the United States and Canada. You can see these black basins that are numbered that go up through it. 24, 26, 27, those are basically all found kind of here in Massachusetts. These are these ancient rift valleys that were left when the Atlantic Ocean started spreading out. And for some reason, the spreading center moved over a little bit to the east. But had things continued as they'd started, eastern Massachusetts and this other microcontinent called the Grenville province would have rifted over and actually been stuck with Africa. And actually, one of the things I also think is interesting is the Massachusetts state rock is this rock called Roxbury pudding stone, which of course you can find in Roxbury, Mass. But things, you can find that same conglomerate rock formation in Senegal and Morocco as well. I just think that's a wild story, where if you look at Massachusetts, first of all, it was constructed by mashing together 3 separate continents. Then as the Atlantic opened up, it started pulling it apart like in the middle, like taffy, but then for some reason that Rift Valley just sort of stopped and moved over to the east. But then much, much later during the ice ages, that's when you start forming like the Cape and the islands. So that's like sediment that was bulldozed down from Vermont and New Hampshire and kind of left there as the glaciers receded. So anyway, the take-home message from this that I want you to have is like all geology is like super local, where geologists will go around to find outcrops of rocks and can get really surprising insights about what the history of the land was like. We had talked before about superposition, the idea that older rocks are toward the bottom of a stack, but the upper strata, if we're looking at sedimentary rocks, are going to be younger. We can make general assumptions then about what the ages of these rocks are, and there are like 3 different ways I want to talk about. The first method we have for putting ages on rocks is what we call relative dating. The idea we can say something's relatively older or younger than another layer, but we don't put a specific age on it. We can do that when the rocks are found in sedimentary stratigraphic layers like this, where they have particular characteristic fossils that go along the way. And so we can also correlate them across great distances. So for example, on the left, you can see that similar rock layers, they represent the similar period of time if they have similar fossil assemblages in them. So we can correlate rock layers across great distances when we have a decent fossil record to include there as well. Then the figure on the right is just, I showed that in the previous slideshow. It's just here to remind me to say that, remember, one of the reasons why fossils are so useful for dating rocks is that we see this directionality in the fossil record. We don't see like reoccurrence or re-evolution of species. We see them kind of happening, I don't want to say in order, but we see characteristic fossils for rocks of particular ages. The other kind of dating that we can do in addition to relative dating is what's called numerical dating. And there are a couple of different ways that we have to be able to work this out. Typically we think of radioisotopes, where we look at radioactive carbon or radioactive potassium or uranium or something like that, minerals that are in these sedimentary layers that we can analyze in the laboratory and be able to estimate how long they've been there based on how they decay. And that allows you to put actual ages on these rocks as opposed to like with years, rather than just saying older versus younger. Now, in this cartoon, there aren't any error bars being shown, but there's always a certain amount of degree of precision that you have to work with when you're trying to do absolute dating. There are some places in the American West where we have a great stratigraphic record. This is the Big Badlands, found in Badlands National Park in South Dakota today. This is where a lot of my research happens. These rock layers, particular red rock layers, and the white ones are actually ash beds. They're ash that got laid down by volcanoes, and those volcanoes have datable minerals in them. So between having characteristic fossils in particular rock layers plus datable ashes in really well-studied areas like here in South Dakota, we actually have a really, really good understanding of what the time frame was for the evolution of these different animal groups. Paleomagnetism is also a way for us to put kind of relative ages on rocks. So if you consider a mid-ocean ridge here, when new rock is being formed, oh, by the way, this GIF here, this is what I think new rock is. This is underwater photography of one of the Hawaiian volcanoes. So this is showing lava getting squirted out right into the ocean and cooling like immediately. The sort of rounded kind of appearance that it has, it's called pillow lava. And actually, you can find pillow lava in Greenfield, Massachusetts. Actually, if you're familiar with Greenfield, you go behind the Big Y Plaza, and there's a rock outcrop there where you can actually see that pillow lava. So volcanism in Massachusetts, something we really don't think about a whole lot. Anyway, the thing is, in addition to doing older versus younger, where we know the youngest rocks are closer to the Rift Valley, what we also find is that the Earth's magnetic poles have not always been the same. So today, for us, magnetic north is the same thing as geographic north, but in the past, what we've seen is evidence that the magnetic pole has shifted so north becomes south for a while, south becomes north for a while. So what's being shown in the figure on the left is so these would be the first rocks that get formed at this mid-ocean ridge, and they start to spread apart. And what's shown in color, those were called the normal periods, meaning when magnetic north was the same thing as geographic north. Here, what we're seeing is that at different time periods, it almost gets laid out like a palindrome, because we remember that there's new rock that's being formed all the time in the middle. When that rock solidifies from a magma, iron minerals that are in there have little magnets in them that are going to orient themselves relative to where north was. So what we see is these repeated kind of palindromic structures as we go from where the youngest rocks are in the middle to where the older ones are before. But they're kind of, this book is getting written from the middle. So what this allows us to do, if we go from what's showing as 0, that would be on the graph on the right, that's showing where the oldest, where the youngest rocks are going to be, and then the oldest ones are going to be in the green toward either side. You end up with this characteristic banding pattern of normal versus reversed in white periods of time. So it's another way to allow you to correlate these together. This doesn't give you exact years on things, though the years being shown there. The reason why we can put ages on those is because we've also combined this with studies of radiometric dating. By studying these radioactive isotopes and how they decay, we look at both. So basically, we look at all three all the time. We have relative aging to kind of check ourselves. We can put ages on rocks to be able to estimate, based on radioactive minerals. But then we can also use the paleomagnetic information in cases where we don't have, good radiometric dating. And in places where we have all three, it's like this Rosetta Stone for us to be able to figure out a good ballpark age for what these rocks are. So what we result in here is, again, using the same color scheme where the hot colors are the youngest rocks and the cool colors, like the blues, are the oldest ones. We have a pretty good understanding of what the seafloor looks like in terms of its ages. And we've done also a lot of work to be able to put together the geochronology of what the land surface looks like as well. A little bit more detailed information here about how radioactive isotopes work. Now, radioactive isotopes are being formed all the time. By the way, I apologize for the Microsoft Paint level of the left side of this figure. But if we consider an element like carbon-14, we know that carbon-14 breaks down at a particular rate. It breaks down into nitrogen-14, so we call that its decay product. So what happens is radioactive carbon is being formed up in the high atmosphere all the time due to cosmic rays and X-rays that are coming from space. That carbon is in the atmosphere and it's going to get taken up by plants. Look at this cycle now. So plants take up that carbon the same way that radioactive carbon, the same way that it takes up regular carbon. And so here we're looking at a slug, a little snail here that's eating some leaves. Takes the carbon that's in that leaf and uses it to build its body. So it emplaces the carbon in the calcite that makes up its shell. after it dies and gets buried and everything, this this calcite shell can get turned into a fossil. It gets completely mineralized. Now, the radioactive carbon is like starting to break down. So what will happen is you can sample a small part of it and then measure the ratio of like stable to unstable carbon to be able to calculate how much time has passed between from when the shell was first built. So anything that's alive that takes in carbon to build its skeleton, like an exoskeleton, like mollusks here, or the endoskeleton that our bodies have, we can use radioactive carbon at least up to about 50,000 years for being able to understand like how much time has passed. So in the cartoon on the right, what this is showing is you start off at the very beginning. So this is showing going from uranium to lead, where if you start off with a rock that has a certain number of uranium crystals in it when it's first formed, after one half-life, you end up with only half of that original amount. After two half-lives, you end up with only half of what you had after one half-life. So you start off at 100%, then you go to 50%, then to 25% after two half-lives, then to 25% after three half-lives, and you get like a characteristic kind of decay that happens. So every kind of radioactive element has a particular slope to this decay curve, but it all works the same way. After one half-life, half of the original parent isotope, the radioactive one, has decayed into some stable end member. After two half-lives, you only have 25%, half of the 50% that you had at the last step. And then down to 12 and a half, and etc. It keeps on going, and you can kind of guess that this is going to get pretty close. The numbers are going to get real small really quickly. After about 10 half-lives, it's not that everything has turned into the stable end member, but basically the radioactive parts are basically undetectable at that point. So for any radioactive mineral, you really get about 10 half-lives out of it before it's undetectable again. If you look at the half-lives for uranium, I mean, this is like a billion years, right? It's really hard to get our heads around these numbers, I think. Once you get to a certain size, any big number is the same as any other big number. So I want to take a little bit of time to think about how these really big numbers compare to things along human lifespans. And to do that, I'm going to talk about this place in New Mexico called the Waste Isolation Pilot Plant. What it does is it's a place where radioactive personal protective equipment is being stored for long-term storage until it's safe again. So up at the surface is where like the surface facility is, but then they tunneled deep down into the rock, into this Salado formation, which is a big, what we call salt dome. This is all halite, like the rock salt that you put on your driveway in the wintertime. And where the person is standing in those like storage chambers in the lower right-hand side, this is all that personal protective equipment that is harmful, is radioactive. We don't want to just keep it at the surface though, because then people can get into it later, because it's going to be dangerous for like 10,000 years. What's going to happen eventually is once the storage chambers are all filled up, they're going to backfill it with rock salt, and then the whole thing is going to basically become continuous with the rock formation around it and kind of sealing it in. So it's going to stay, there. This is a hard problem. It's a hard problem because in order to have signage that's going to last for 10,000 years, then we need to find some kind of system to tell people this isn't natural, we're not hiding something that's valuable, and it can kill you but not kill you immediately until a certain year, because who knows what calendar they're going to be using. You can take a minute to pause the video to read this if you want. I'm not going to read it to you. It's one thing to say, well, we'll put it in English and Spanish and stuff or whatever, and then figure that people will be able to avoid it. But the interesting thing I think about this problem is that the way that the United States government went to try to solve this problem was to involve not just engineers and scientists, but also linguists and anthropologists and architects to be able to think about how we can send a complicated message like this, like assuming the worst case scenario. Let's imagine that global human population is down to like 1/10 of 1%, and the people like roam the landscape Mad Max style in little nomadic bands. How are you going to send that message to these people if there's like no continuity of knowledge? I mean, think about it like this too, because like this is Beowulf. This is about 1,000 years old. This is Middle English. Now, you can basically read this, but it looks really different after only 1,000 years. And that's 1/10 of the amount of time we're trying to account for here. This is the English alphabet and how it's changed over the last 3,700 years. So over this period of time, again, about 1/3 of the amount of time that's going to elapse between when the waste isolation pilot plant is sealed up and when it's going to be safe, we see this kind of change in our alphabet. So how do you send this message over these kinds of time frames if cultural evolution happens so fast? So there are a few approaches taken for this. I'm going to have a couple of slides of concept art for ways that things that might occur up at the surface. For example, you want to show that this is like foreboding, that it's menacing, but also that it's not natural. It's going to be human-made. So whether it's a spike field, or actually I like the spikes bursting through grid because it shows a non-natural kind of layout here, and also showing that this is a place that you would want to avoid. There should be places made out of durable materials that are going to have information in as many languages as possible, and also to invite whoever gets there to translate it, if possible, into whatever language they speak. Another thing you can do is, you can't just put scary faces up, but you want to convey that this place will make you sick. So, you probably recognize up the top, and that's the scream from Monk. But these faces down here, another thing that Darwin did is he was interested in the study of the expression of emotions in people and animals. And he found that people can tell the difference between a face that means frightened as opposed to a face that means you've been made sick. People have tried to put scary faces on tombs of royalty for thousands of years, but grave robbers just learned that you're hiding something good. What we want to convey is the message that you don't want anything that's here. This is stuff that's dangerous. We're not hiding treasure. Or even to convey to somebody who might not be literate or might not have any scientific knowledge. Basically, when you see this radioactive trefoil symbol, it's a notice here. So it's like, okay, you touch the radioactivity and it gets on your body, but then you notice when the tree's taller, like when it's when more time has passed by, that it makes you sick later. A further problem is to figure out what year it is. Now, we know that the stars in the constellations that we see today those stars are in motion. So, that the Big Dipper used to look different than it does today, and it's going to look different in the future based on what the tracks of the stars are. So they had proposed some kind of dating system, basically, where, okay, you put your head here and you look up at the stars at night, and if Polaris the North Star is no longer the center, then it's still too close in time. But if the stars look like this in 12,000 years after closure, then that's showing that, okay, enough time has passed that the stuff here is now inert and not harmful. I just think this is a fascinating problem. Part of the reason because it tries to work with a lot of different ways of knowing than just science and engineering. If you're interested, I have short versions as well as the full versions of the reports that they're trying to crack this problem. If you want to check them out on your own, they're in the learning module. In the end, our studies of rocks and fossils have given us the geologic timescale. Now, the geologic timescale is primarily based on fossils. It's based on extinctions found within the fossil record. So it's actually really a biological timescale, even though we apply it to rocks. And if we zoom in on just the most recent part of the geologic timescale, so up at the top of this age, that's today, that little thin sliver called the Holocene, that encompasses the great majority of our species' existence. And that amount of time is the amount of time that represents like how long it's going to take for the WIP area to be safe. All of these other names are subdivisions that are based on fossil assemblages, usually marine ones. And you can see along the side the black and white banding pattern. That's again showing like the normal versus reversed magnetic intervals. So it's been a long time coming to generate the full geologic timescale, and it continues to be made more precise over the years. But this is part of the story of how we understand like what the age of the Earth is, so we have a real solid understanding of how long we have for evolution to happen.